Now let's start with the first topic, the concept of simple stresses and strains. So see the first question. A free bar of length L, this is L meters, is uniformly heated from 0 degrees Celsius to temperature of T degrees Celsius. That means some temperature changes we are providing for the bar. Alpha is the coefficient of linear expansion and E is the modulus of elasticity. Then the stress induced in the bar. Now, whenever we are providing the temperature changes, definitely member is experiencing the strain. But when that strain is prevented, either completely or partially, then only the member is experiencing the temperature stress. But here, clearly mentioned, it's a free bar. That means there is no resistance against the thermal expansion. When there is no resistance against the thermal expansion, then stress will be equal to 0. Obviously, due to free expansion. Why it is 0? Due to free expansion. Clearly mentioned, bar is a free bar. No thermal stress induced in the bar. No thermal stress induced in the bar. So, which option is correct? Option C is correct for this question. Now, let us consider the 2 marks questions from this topic. See the first question. It is one of the interesting question. Here, we are involving 2 concepts. Temperature changes as well as a buckling effect in this particular problem. Read the question. Determine the temperature rise necessary to induce buckling in a 1 meter long circular rod of diameter 40 mm. Diameter is given, length is given, shown in the figure. Assume the rod to be pinned at both ends. This side and this side we are providing the pinned support. And the coefficient of thermal expansion as 20 into 10 raised to minus 6 per degree Celsius. Assume uniform heating of the bar. Now look at here. Here, whenever we are providing the uniform heating, obviously bar it is expanding in this direction. But look at here. If I want to buckle, if I want to develop the buckling of this particular buckling phenomenon in this particular rod, up to what value of temperature I need to increase in the particular bar. That is asking at what value of T we are expecting the buckling mode of failure in the rod. Buckling is related to the slender members. Now, if I want to observe the buckling phenomena in case of slender members, already we know we are using a Euler standard formula. PB equal to pi square E I min divided by LE square. That's fine. But here we are not using any external force. We are doing only temperature changes. So when temperature changes are given to the member, it causes the strain in the member. When that strain is prevented, here we are preventing the strain by using these 2 pinned supports. Obviously, what happened, my dear friends? Stress will be generated. That stress, it is causing the thermal load. Thermal load, it is nothing but thermal stress into cross-sectional area. Thermal stress, when both ends are completely prevented of the expansion, then we are know that it is E alpha del T into A. That's fine. So, because of temperature rise, whatever the thermal load we are observing in the bar, when it is exactly equal to the buckling load, Euler buckling load, we are expecting the buckling mode of failure. So, apply this condition at equilibrium condition. At equilibrium condition, let us take this one. This thermal load, it should be equal to Euler buckling load. Thermal load, it is E alpha del T into area. PB, it is pi square E. In place of I mean just I am writing I. LE I am writing as L. Why it is L? Both ends are clearly mentioned as a hinged one. And that 1 meter I am taking in terms of millimeter. That's it. Other data directly I am writing in this equation. It should be, so this should be equal to, both are equal. Both are equal, my dear friends. Both are equal. That's fine. Now substitute the values one by one. E alpha del T area of the rod is pi by 4 T square. And pi square into E into I can write it as pi by 64 D raised to 4 divided by L square. That's it. If any terms are getting cancelled, first you do the cancellation. Here E getting cancelled. Here pi getting cancelled. D square here we are observing. D to the power 4 we are observing at here. It is a D square we are having. That's fine. Here 4 we are observing. Here it is a 16. Right? Now, what we required? Del T. Del T. Bring this term this side. Here first you take these terms. Pi square divided by L square into D square divided by 16 into 1 divided by alpha, na? Obviously, 1 divided by alpha. So, you can substitute the values. Pi square divided by L square, 1000 square into D square. What is the D value given? 40 millimeter. 40 millimeter. 40 square divided by 60 into 1 divided by how much? 20 into 10 raised to minus 6 alpha value. 20 into 10 raised to minus 6. That's it. Simplify this one. Pi square divided by 1, 2, 3, 4, 5, 6 into 1600 divided by 16 into 1 by 20 into 10 power minus 6. This one is getting cancelled. Na? 1 0 getting cancelled. Na? This is 10 na? And this is 5. Na? Pi square into 5. Approximately it is of 49.6. You can verify it. Final result. So, finally we are having 49 del T value. We are having a 49.6 degrees Celsius. That is causing the buckling in the rod. This temperature change, it is causing the buckling in the rod. Hope you understand this problem, right? Let's move on to the next question. This is arrangement of the bars in parallel connection. Let's take this one here. See the question first. Below figure shows a rigid bar hinged at A and supported in a horizontal position by two vertical identical steel wires. So, this is a rigid bar clearly. Just I am writing RB, rigid bar. And these two are steel wires, my dear friends. These are steel wires. Both are steel wires. That's fine. We need to keep these wires to provide the horizontal position for this rod. Neglect the weight of the beam. That is nothing but weight of the rod. Self weight of the rod you do not consider. The tension T1 and T2 induced in these wires by a vertical load P applied as shown in the figure. Look at here, where the load is applied? Here. Here. This is P. That is the load. Now, this is L units and this is L units. And the tension in the first wire is T1, tension in the second wire is T2, and clearly mentioned this distance is a B and this distance is a A. Here we are providing the hinge support. That's fine. So, let me take the FBD of this one. When I am taking the FBD of this one, just you can take this is, here we are having clearly, rod I am showing first. Here we are having a hinge support. I can mark this as point A. That's fine. Now, load P is placed at here, middle of this one. Now this is the load P position. Here to here distance it is L, and here to here distance L we are having, that's fine. And let me take the two steel wires, one wire we are having at here, one wire we are having at here. Let us consider this is T1 at a distance of A units, and here we are having T2 at a distance of B units, that's fine. From hinge support, right. What we required, T1 and T2. Generally, to find out the unknown reactions, we are using equilibrium equations. Here I am following that equilibrium equations. Now, let us take if this rod, if this P, it is pulling the rod in downward direction, something like this, then these two steel wires will try to keep the rod in the horizontal position. When these two steel wires will keep the rod in a horizontal position, they are experiencing some tension, T1 and T2. That only I need to find out. Now, what is the effect of P on this rod? It is causing the inclination of the rod, something like this, initial position, obviously. So, this is the inclination we are observing at this second wire. This is the inclination we are observing in the first wire. Let me take that inclination I am showing with del L1, my dear friends. Why? Y means how much inclination we are observing, the same amount of deformation we are observing in the first steel wire. Similarly, here also I am taking this as a del L2. That's fine. Del L2. Right? Fine. But our requirement is T1 and T2. For that first initial I am using a moment equilibrium condition. I am balancing the moments about A, my dear friends. Clockwise sense of rotation I am taking one side, anti-clockwise sense of rotation I am writing other side first initially. Let's see. Now this is giving anti-clockwise sense of rotation. P at a distance of L. It should be equal to T1 at a distance of A plus T2 at a distance of B. I can mark this as equation 1. Because T1 and T2 both are unknowns we are having. Now, let us take the similar triangles. Now, this is one triangle we are having. And this is the other triangle we are having. These two similar triangle concept I am using. These two. From similar triangles, what is our observation? From similar triangles, let us take del L1 divided by, or you can take del L1 divided by this one, divided by this part, A equal to del L2 divided by B. That is our observation. That is our observation clearly. Now, how I am rewriting this one? Del L1 into B. Del L1 into B equal to del L2 into A. Just I am writing. It is nothing but axial deformation, na? Obviously. Axial deformation formula, you know, standard formula, PL upon AE. So, how I am writing this one? T1, what is the length? Length is same for both wires, clearly given. L divided by, you can take that as a AE, that's fine, into B. Come to the del L2, T2, L divided by AE into A, that's fine. Right? Now, AE is getting cancelled because both are made of same meter and same area, that's fine. Length is getting cancelled, my dear friends. Length is getting cancelled. Then T2, if I take this one, or you can take T1, your wish. Your wish, any one of these things you can take. Here I am writing T1 equal to, I am writing T1 equal to T2 into A divided by B. T2 into A divided by B. This is we are observing T1 value. T1 value we are having T2 into A divided by B. This value you can use in this equation. If I use it, P into L equal to P into L equal to, that's fine. T2 in place of T1, I am taking T2 into A by B into A plus T2 B we are having. That's na T2 B we are having. T2 B na, obviously. B, yeah, that's fine. Right. Now T2 you can take it as common. A square by B plus B. Now T2 A square plus B square divided by B. P into L. T2 value how much we are having? P L B divided by A square plus B square. T2 value we are having PLB divided by A square plus B square. Similarly, if I do this one, I can usually find out the T1. T1 PL in place of B we are having A divided by A square plus B square. This is the T1 value. That is the T1 value. See this one, T1 PLA PLA divided by A square. This is absolutely wrong. Absolutely wrong. T1 PAL divided by A square plus B square. T2, yes. If you are observing, option B is correct. Option B is correct. Only that values only we are having. So T1 PLA divided by A square plus B square. Observe this one. PAL divided by A square plus B square. T2 PLB divided by A square plus B square. So which option is correct? Option B is correct for this question. When we are observing this question, very long back, 94, right? Let's move on to another topic, complex stresses and strains. This is one of the important topic from the examination point. Frequently we are having the questions from this particular topic. Most probably just numerical based questions only we are expecting from this topic. Let us see the first problem. An elastic body is subjected to a tensile stress X in a particular direction and a compressive stress Y in its perpendicular direction. Here we are observing member is subjected to the biaxial state of stress with the tensile nature in one direction and the compressive nature in perpendicular direction. X and Y are unequal in magnitude. They are not equal, but they are opposite in nature, unlike in nature. On the plane of maximum shear stress in the body, there will be no normal stress. The plane which is carrying the maximum shear stress, on that plane, out of these four options, which is correct option. Second option, if you take also the maximum normal stress, plane of maximum shear stress, it is also carrying the maximum normal stress, that is option B. Option C, the minimum normal stress becomes minimum, and here both normal stress as well as shear stress out of these two. So first of all, you take the state of stress for this element. When I am taking the state of stress, here clearly we are having a biaxial state of stress. Biaxial state of stress. This is the element I am taking. Now on this element, let us mark the stress in X direction. Tensile nature is given. That is given as X units. The stress in Y direction, it is given as compressive nature. Stress, this magnitude, it is given as Y. X is not equal to Y, clearly mentioned. So I can take this as, just imagine, suppose if it is 10 units, if it is 10 units, and this you can take 5 units. Both are unequal in magnitude. Let us try to solve this question. Out of the four options, which option is correct? To solve this question, I am using the Mohr circle method. To use the Mohr circle method, if I want to plot the Mohr circle, What are the basic parameters I require? First parameter I required is the distance from origin to the center of Mohr circle. Distance from origin to the center of Mohr circle, that I can take it as a OC. How you can find out this one? As we know the standard relation, sigma x plus sigma y divided by 2. Sigma x is a plus, sigma y is minus 5. Why? Clearly it is having compressive nature. Sigma x equal to plus 10 units I am taking. Sigma y equal to minus 5. Both are unequal, clearly mentioned. Divided by 2 we are having. This is 2.5. Very good. Second parameter I required, radius of Mohr circle. Radius, how should I find out? From in-plane maximum shear, I am getting this one. Sigma x minus sigma y divided by 2 whole square plus tau xy square under root. There is no shear. This is clearly biaxial state of stress. Then it is 0. From here, if I take this one, R, we are having 10 minus of minus plus divided by 2 whole square. 15 divided by 2. That is nothing but 7.5 units. With this information, when I try to plot the circle, how it could be is, now let me take, when I am taking the circle, when I am plotting the Mohr circle, on x-axis we are taking normal stresses, on y-axis we are taking shear. Very good. Now when I am speaking this one, here we are having normal stress. Here we are having this side shear with clockwise sense, and this side shear with the anti-clockwise sense. I can use it. Very good. This is the origin point. Now OC, here we are having a 2.5 units. Just mark somewhere at here 2.5. Here I am taking this is 2.5. I am having. Radius, how much we are having? 7.5. Obviously 7.5 is more than 2.5. So somewhere you can take it. Here this is. I can mark this point as A. From here to here it is giving the radius. This distance, it is giving the radius distance. With the C as center, AC as a radius, if I take the circle entered into the negative normal axis side. The circle is something like this we are having. End points of the Mohr circle on x-axis, it is giving principal stresses. Now OB, it is giving one principal stress. Let us mark this as a sigma 2. OA, it is giving another principal stress. Let us mark this as sigma 1. This is one principal plane. This is one principal plane. The angle between principal plane and tau max plane, it is a 45 degrees. That also shown as 90 degrees in Mohr circle. Now when I am identifying the tau max plane, this is tau max plane. Let us mark this as C. CD, this radial line, it is representing the tau max plane at an angle of 90 degrees, anti-clockwise direction. Now what is the x coordinate for this one? If I take the radial line and if I take the point corresponding to the radial line, x coordinate, it is giving the normal stress value. Y coordinate, it is giving the shear stress value. X coordinate, it is giving normal stress value. Y coordinate, it is giving shear stress value. This is. So what is the normal stress at here? This is. Normal stress at here, it is a 2.5. And in addition to tau max, it is nothing but radius, na? Obviously 7.5. So both normal as well as shear stresses are acting. But here the maximum normal stress is this one. Maximum normal stress is OA, minimum normal stress is OB. So obviously on tau max plane, we know that on tau max plane in general both normal as well as shear stresses are acting. And if I take the state of normal stress, it is a neither maximum nor minimum. Obviously, which option is correct? Here this option is ruled out. Normal stress, it is not becoming maximum. Normal stress, it is not becoming minimum. Option D is correct for this question. Which is correct option? Option D. So hope you understand this question. We can solve this by using analytical method also. Here I am using a Mohr circle method. Let's move on to the next question. A cylindrical elastic body subjected to the pure torsion about its axis develops. Here the member is subjected to the pure torsion. Pure torsion, it will develop a pure shear condition. Pure shear condition. Pure torsion, it will develop the pure shear condition. So as we know, under pure shear condition develops diagonal tension and diagonal compression. Already we know that. Develops diagonal tension and diagonal compression, obviously. Now, and in this case, sigma 1 equal to minus sigma 2 equal to tau max, we know that. Both the principal stresses are equal in magnitude and opposite in direction, and the magnitude, it should be equal to tau max for this condition. Now, here 4 options we are having. Read the 4 options. Tensile stress in a direction of 45 degrees to the axis. Absolutely, that is correct. No tensile and compressive stress. Exactly. Look at here. Here we are having this condition will develop diagonal tension and diagonal compression. So this option is ruled out. Maximum shear stress along the axis of the shaft. Under pure shear condition, if you take a shear distribution, it is 0 at center of the shaft. Maximum at extremities, circumference, that is at a circumference with the linear variation, as we know that. Here we are having this one. Let us take, if I take this one, here applied torque, that is going to be resisted at this end. If I represent the state of stress for this condition, this is the state of stress. As we know, this is state of stress. We are observing along this diagonal, tension develops with tau, because this is tau, maximum. Along this diagonal, compression develops, but magnitude is same. Compression develops, magnitude point, both are same, right? Now, this is the case we are having. So, if I take the shear distribution, shear stress distribution, as we know, shear stress distribution, here we are having maximum shear. Here we are having maximum shear. At the center, it is 0. Ruled out that. Maximum shear stress at 45 degrees to the axis. No, here we are observing diagonal tension and diagonal compression. So, which one is correct? Option A. Exactly. Tensile stress develops on 45 degrees. This is 45 degrees axis. Exactly. If I take this one here, we are having. Exactly. If I cut this one, 45 degrees we are having. Diagonal planes, 45 degrees. Option A is correct for this question. Option A. Let's move on to the next question. See the question. This is another straightforward question. If the two principal strains at a point are 1000 microns and minus 600 microns, then what is the maximum shear strain? So, major principal strain here it is given as 1000 microns, and minor principal strain it is minus 600 microns compressive nature. We required pi max. How should I find out the pi max? Maximum shear strain, as we know, epsilon 1 minus epsilon 2. Epsilon 1 is 100, 1000 minus of minus 600 into 10 raised to minus 6. Direct answer. It is nothing but 1600 microns. Maximum shear strain in this case is, under this condition, is 1600 microns. This is a formula based question. 1600 microns we are observing at number C. Option C is correct for this question. Yes, now we can take the 2 marks questions from this topic. Take the first problem. This is a GATE 90 very long back question. The 3-dimensional state of stress at a point is given by, yes, given element is a 3-dimensional element. We require the shear stress. We required the shear stress in XY plane at the same point is then equal to. So, when I am taking this is a direct question, very simple question. Compare this with the standard tensor matrix for 3-dimensional element. In stress tensor matrix, normal stresses we are placing along the diagonal. shear stresses we are placing above and below the diagram. Here this is tau xy, this is tau xz, this is tau yx, this is tau yz, this is tau zx, this is tau zy. Very good. What we required? We required this one, tau xy, clearly mentioned. Tau xy or tau x. This is we are observing in xy plane. Now, where you are identifying this component in this matrix, now look at here, 10. So, tau xy equal to positive 10. Positive 10 mega Newton per meter square. So, which option is correct? Option C is correct. It is simple question, but 2 marks question. Option C is correct, right? This is 2 marks question. Let's move on to the another question. Very interesting question. Next one. Read the question carefully. Read the question carefully. At a point in a stressed body, the state of stress on 2 planes 45 degrees apart as shown below. The angle between these 2 planes is given as 45 degrees. From vertical plane, this oblique plane, it is making an angle 45 degrees in incline, 45 degrees in anti-clockwise direction, counterclockwise direction. So, this is our reference plane. This is our reference plane. Very good. What we required? Determine 2 principal stresses. With this information, you can determine 2 principal stresses. Let me mark this as a x direction and this is y direction. What is the data given from this triangular wedge? You try to extract that data. This is sigma x na. So, sigma x it is given as, just I am writing, sigma x it is given as positive 8 megapascal. Sigma y we need to find out, because whether it is there or not we can check it. Sigma y is there or not, I don't know, just we need to check it before calculating the 2 principal stresses. Tau xy is given. On this face tau xy we are having in downward direction. As per our sign convention, this is nothing but minus value as per our sign convention. And here if I take this one, this is taking a clockwise rotation. This shear, this tau 45 degrees, this is sigma 45 degrees, right? This is taking clockwise rotation. Clockwise rotation of shear onto the reference plane we are taking as negative na? Absolutely. Tau 45 it is minus 3 megapascal. And sigma 45 it is plus 2 megapascal. What about the angle? Here angle either positive or negative, as it is giving anti-clockwise rotation. Anti-clockwise rotation theta we are taking that as a positive na? Yes, positive value we are having. That is the data we are having. From this data, before finding the 2 principal stresses, whether sigma y is existing in this case or not, first you verify it. After that only we need to find out the principal stress. But how should I find out that? Yes, this is the data useful for us to find out any one of these. Either you can use this one or you can use this one. Any one of these is sufficient to get sigma y value. How? As we know how to find out the stresses on inclined planes, I am taking that. Sigma on 45 degrees plane equal to sigma x plus sigma y divided by 2 plus sigma x minus sigma y divided by 2 cos 2 theta plus tau xy sin 2 theta. What is sigma 45 it is given? Sigma 45 is given as 2. Sigma x how much? Sigma x is 8. Sigma y we need to find out whether it is there or not, plus 8 minus sigma y divided by 2 cos 90 degrees plus tau xy minus 3 sin 90 degrees. Very good. You can strike off this term. Cos 90 is 0. Then if I simplify that, 2 equal to 4 plus sigma y by 2 minus 3 we are. 1 into 2, 2. Finally, y, sigma y equal to we are having 2 megapascal. Yes, sigma y is there. Sigma y we are having 2 megapascal. This value you can use in the standard principal stresses formula. We require the principal stresses, both principal stresses. Sigma 1 and 2 equal to, what is the standard relation we are having? Sigma x plus sigma y divided by 2 plus r minus under root of sigma x minus sigma y divided by 2 whole square plus tau x square. Everything is known. Just you can substitute and simplify, you are getting answer. Sigma x it is given as 8, sigma y it is given as 2 plus r minus under root of 8 minus 2 divided by 2 whole square plus minus 3 whole square. If I simplify, how much you are having? 10 by 2 is 5 plus r minus this term, if I take this one, it is 4.242. Then sigma 1 equal to 5 plus 4.242. Sigma 2 equal to 5 minus 4.242. This is, if I take this one, 9.242, and this is 0.75. Just take this. These are the magnitudes of the principal stresses we are having in this particular problem, right? For this case, this is NAT type question. Hope you understand this question, right? Now we are going to be solve the numericals from other topic, that is SFD and BMD analysis in case of beams. First, let you take the one more questions. See the first question. This is an good GATE 89 question. Very long back question. But take the question. For a simply supporting beam on two end supports, the bending moment is a maximum. Here asking a bending moment location for a simply supported beam. So, I am having a simply supported beam something like this. Supports we are providing at end corners. Under loading condition, bending moment should be maximum where? Option A, if you take usually on the supports. Option B, always at midspan. Option C, where there is no shear force. Option D, where the deflections is maximum. When I am speaking about the first option, usually on the supports, bending moment is always 0 at the supports, because both roller and hinge support can permit the rotation. Obviously, MA and MB is 0. First option is a strike off. Always at midspan. This is also a controversial statement because the magnitude of the bending moment will be depends on the nature of load as well as the supports that we are providing for the beam. Now, when I am taking the third statement where there is no shear stress, yes, shear force, we are having the relation between bending moment and shear force, that is dm divided by dx equal to shear force. When I am taking the first derivative of this one and equate it to 0, bending moment equation, you can take the first derivative and equate it to 0, then you are getting from these two relations, what is our observation? F equal to 0, where shear force is going to be change its sign. There we are expecting the bending moment to be maximum by its magnitude. So, option C is correct for this statement, right? Hope you understand this question. Let's move on to the next question. See the next question. A block of steel is loaded by a tangential force F on its top surface, while the bottom surface is held rigidly. Here we are having the fixed support and here we are having a tangential force. From this data, what we require, the deformation of the block is due to. So, if the load is causing the deformation in the block, the deformation is because of shear only, because of bending only, because of shear and bending, and because of torsion. Which force is responsible for the deformation in this particular block? try to observe the effect of this P or force F on the block. When I'm speaking about this one, just it is if you turn 90 degrees, it is looking like a cantilever beam. Now, when I am observing the effect of this one load, it will be acting something like this. It will try to bend the block like this. This is the final deformed position of the block about fixed support. When it is bending, here we are observing two effects at a cross section of the beam. One, shear force effect. Deformation it is causing because of shear force as well as because of bending moment. Two types of effects we are observing because of F at the free end of the block. So, here deformation we are observing because of shear as well as bending. Option C is correct for this problem. Hope you understand this question. Let's move on to the next question. Read the question carefully. A concentrated load P acts on a simply supported beam of span L at a distance of L by 3 from the left support. Given beam, it is a simply supported beam. Type of load is the point load. It is acting at a distance of L by 3 from the left support. First, you let you take that beam. This is a simply supported beam. And where the load is placed? Load is placed somewhere at here. I can mark this as point C. Here we are applying a load P. And this is at a distance of L divided by 3. If it is L divided by 3, total span of the beam it is given as L units, then this distance it is 2L by 3. I am assuming it is A and this is B, my dear friends. B equal to 2L by 3. The bending moment at the application of load should be, we need to find out the bending moment. Where? Here. Bending moment I need to find out at here. That's it. At the application of load, that is nothing but at point C. So, how you can take the bending moment at any section? Simply we are applying the either side concept. Algebraic sum of the moments either left of the section or right of the section, it is giving the bending moment at that particular section. Suppose if it is point A, so to write down the bending equation, first I require the magnitude of RA. How I am getting the RA value? RA generally W, generally reactions we are getting from the equations of equilibrium. Here I am using the standard formula, that is a WB divided by L. What is the W in this case? W, it is nothing but P. B value, it is 2L divided by 3 upon L. This one is getting cancelled. 2P divided by 3. That is RA value. Once I have this one, bending moment at C, if I take, that is RA at a distance of L divided by 3. RA value we are having 2P divided by 3 into L by 3. Simplify this one, you are having 2PL divided by 9 is the required answer. Where we are finding this value? At number B. Option B is correct for this particular problem, right? So, let's move on to the another question from this chapter. 2 marks questions from this chapter. This question is again very long back question, 96 question. Try to read the question. 2 bars AB and BC. This is AB segment and this is BC segment, right? Are connected by a frictionless hinge at point B. Here we are having hinge point. At B we are having a hinge point. The assembly is supported and loaded as shown in the figure. Here at this point we are having 100 kilonewtons. At this point again we are having 100 kilonewtons. Let me mark this as a point D. I can mark this as point E. At these 2 points we are observing point loads 100 kilonewtons, 100 kilonewtons. Draw the shear force and bending moment diagrams for the combined beam AC. So, for this internal hinged beam, we required a evident BMD clearly labeling the important values. That means at each section, you try to represent the shear force value as well as bending moment value. Also indicate your sign convention. This is somewhat conventional mode question, but very long back it is given. Generally, these type of problems are nowadays they are not asking in the examination. Directly they used to ask the shear force value or bending moment value at one particular point. Right? How to proceed this one? Now, first of all, as we know, first this support, fixed support we are having. Fixed support, it will give vertical reaction as well as reactive movement, reaction movement at A. I can say it is RA. Here roller support we are observing, that is giving reaction RC. So, my first target is finding the reactions. Then we can carry the shear force analysis as well as bending moment analysis. But how should I proceed? Now, let me take at internal hinge. As we know, at internal hinge, bending moment will be 0. So, you try to write down the bending equation by taking the section at a B, consider the forces right hand side of your section. Right hand side of your section. Then automatically we are eliminating the effect of RB, rotation effect of RB at a B. Write down the bending equation. When I am taking the bending equation, RC, it is at a distance of 4. Here 1, 1, 2, total 4. Now, how it is giving the rotation? Sagging effect. That's why I am taking positive value. 4. Very good. Then as I move on from C to E, here we are observing 100 kilonewtons. This is giving hogging effect. What is the distance from here to here? 3 meters minus 100 into 3. Good. Then one more 100 is there. That is also giving the hogging effect. How much the distance here we are having? This is a 2. Let us take that is a 2. Altogether 0. So, from this one, try to find out the RC. When I am finding the RC we are having how much, my dear friend? 125. Just to simplify this one, you are having RC 125. RC 125 kilonewtons. Once I have the RC, then try to find out RB also. Let us take this one. RB plus RC equal to how much? 200 na? This is for the part BDE. If I take this one, my requirement is this one, RB. So, you can assume it is a simply supported beam. Here 2 point loads are there. They are acting downward direction. RB and RC are upward forces. You apply the force equilibrium condition for part B, D, E, C. You can take summation of forces. You can balance the forces along y direction. Upward force I am take it as positive. Then RB plus RC equal to 200. Already we are having RC value, then RB equal to 200 minus 125. This is 75 kilonewtons. Now we are having a RB. Here RA is not required. Without RA, I am getting the shear force and the bending moment. Try to take the shear force analysis. When I am speaking about the shear force analysis, the given beam if I take, the given beam is something like this. This is the given beam we are having. Here A, here B, D, E, C. Here 100, here 100, here RB, here RC. Good. Now, when I am taking the distances, 1.5, 211. 1.5 meters, 211 we are having. Directly I can plot the shear force. When I am taking the shear force diagram, let us take first the length of the beam. Just I am taking the length of the beam. This is shear available at point C. That is nothing but RC na. RC value how much we are having? RC we are having 125. RB we are having 75. Here negative. Let us use this one. Negative shear. Here we are having, this is point C. This is point D. This is point E. Shear available at C is 125 RC. Negative. From here to here, there is no load variation. From C to E, there is no load variation. Then I can move at here. Again, at E, we are observing a downward force. It is a positive. Minus 125 plus 100. How much? Minus 125 plus 100. It is minus 25. Just one step. It is moving. One step. It is moving up. Something like this. Here the shear available is 25, still it is a negative, and from here to here there is no load variation, then it is moving horizontal, and at a D again minus 25 plus 100 plus 75 na, then it is taking a rising shear. Rising shear, if I take rising, it is giving to rising 75 from here to here, and again there is no force variation. At B also we are having a 75. This is going to be balanced at here. RA same. Here we are having RA equal to 75 we are having, right? So how much shear is available at here? This is 75. This is point A. This is point B. This is point C, point D. This is point B, and this is This is 75, this is point B, this is point D, and this is point E, and this is point C. Right? All features we are locating. Positive shear I am taking here above the line, and negative shear I am showing it here. This is the correct representation of a shear force diagram. Now, similarly, you try to plot the bending moment diagram. When I am speaking about the bending moment diagram, let us take first the length of the beam. This is A, and here we are having C, my dear friends. Now, try to take this one. First, I will try to find out the shear force at C. It is 0. Sorry, bending moment at C, it is 0. Bending moment at E, how much? Bending moment at E, if I take this one I am taking. RC into 1 na? RC it is 125 kilonewton. Positive or negative? Positive. Sagging effect. At C, it is giving a 125. At E, how much bending moment is available? 125 kilonewton meter. This is all in kilonewtons. Good. Now, my requirement is a shear available at, bending available at D. Take the section at D and try to take the right hand side forces. When I am taking right hand side forces, 125 into 2 is 250, positive 250, minus 100, minus 100. 250 minus 100, how much? 250 minus 100, it is a positive 150 here. Positive side only, linear variation. Here we are having a 150 kilonewton meter. Right, this is at D. At D we are having. Good. Now, when I am taking at B, obviously at B, bending moment is 0. Here I am locating that B. You can take this one. Then what is the bending moment available at A? 75. 70. Take the section at here and take this section. Here, this part you can consider, this part you can consider to find out this one. 75 into 1.5. Bending moment available at A is RB into 1.5. 75 into 1.5, approximately this is 112.5 linear variation. Here we are observing POC, right? This is the bending moment available at A with the hogging nature. Here we are having positive nature. This is BMD, my dear friend. All features we are just writing on a subdend BMD. This is a somewhat conventional mode question, but very long back this was given. You try to solve this kind of models also, right? Now let's move on to the next question. Read the question carefully. This is again very long back we are having. 97. A mass of 35 kg here is provided. 35 kg is suspended from a weightless bar AB, which is supported by a cable CB. CB we are having cable, tension on the cable clearly mentioned, and a pin at a point A. Here we are having the pin support. Here we are having the pin support. The pin reactions at A on the bar AB, we need to find out the pin reactions. This is X direction, this is Y direction. Rx and Ry at point A we require. So, how much mass we are having here? 35 kg. That if I take in Newton, this is 35 into 9.81 Newtons we are having. We need to find out. So, first to take the free body diagram of AB. When I am taking the free body diagram of AB, this is we are having at A, this is A and this is B we are having, right? Now, at a B we are having a string or a cable, what we call it as cable. Cable tension, how is it is acting? Cable tension, it is acting like this. That is the tension we are having in the cable, and the weight or the mass we are having something like this at this end. Here we are, right? These are the loads we are having. W equal to how much? 35 kg into 9.81 newtons. Good. This is the theta we are having. This is the tension we are observing in the cable when it is carrying W mass. Now, let me take here. If I am having this one, right? So, we require the reactions at pin A. Pin A, it is a giving two reactions, that is Ry and this is Rx, clearly mentioned XY directions we are having, right? Now, what is the length of this one? It is given as 275 millimeter length of this one. So, first of all, this tension what we are observing on the cable, you can resolve this along X direction, along Y direction. When I am observing this one, so I can resolve this along X direction, along Y direction. When I am speaking about this one, let me take first that one. Now, this is Y direction we are having, and this is we are having in X direction, that string. This is T cos theta and this is T sin theta, this component. So, how should I get theta value? Now, look at this one. Consider this is a right angle triangle, simple geometry. This is a right angle triangle. Use this concept from the right angle triangle, tan theta equal to 125 divided by 275. Is it right or not? Exactly. Then theta equal to 24.44 degrees. Theta we are having this one. Theta how much we are having? Theta we are having 24.44 degrees. Good. Now let us use this one. Now theta value I am having simply. Then T is unknown at here. Is it right or not? T. W is there here. T is unknown at here. This is a axial component, horizontal component. This is a vertical component we are having. Now how should I proceed? To get the reactions, unknown reactions, we are using equations of equilibrium. Here I am using first a moment equilibrium condition. I try to balance the moments of all forces about A, my dear friends. Your wish, you can apply the force equilibrium condition. Summation of forces along x is 0, summation of forces along y is 0. Obviously, like that also we can get it. Right? Now I am using this one. Summation of moments about A equal to 0. Clockwise rotation I am giving positive. Now how many forces we are having? You try to observe about this one. Here and here. You can take that. When I am speaking this one, first I am taking this one W. Right? W you can take. And W it is giving the clockwise rotation. W at a distance of, if I take 275, this is 275 mm, W to 275 mm clockwise minus T sine 24.44 degrees into at a distance of 275, my dear friends, 275. It is anti-clockwise direction. It should be equal to 0. Very good. Now here 275, here 275 is getting cancelled. If I simplify that, then what is the value we are having? T equal to, directly I am getting unknown value, that is a T. T. Bring this on this side, W divided by sine 24.44 degrees. W divided by sine 24.44 degrees. What is W? 35 into 9.81 divided by sine 24.44 degrees. If you simplify, how much we are having? 830 newtons. So tension in the cable we are observing 830 newtons. 830 newtons, that is the tension available. But we do not require tension, we require the reaction Rx and Ry. Now use summation of forces along x equal to 0. When I am using summation of forces along x equal to 0, then take this one. Here we are having Rx towards right, T cos theta towards left. Rx equal to, I am writing Rx equal to T cos theta, my dear. T how much we are having? 830 cos 24.44 degrees. Now how much we are having? If you simplify this one, Rx we are having 755.4 newtons. 755.4 newtons Rx. Look at this one, Rx 755.4 newtons. We are observing Rx. Strike off this at a C and at a D we are having. That means either C or D is correct. Either C or D is correct. So we need to find out Ry. So again you can use the force equilibrium condition along y direction. Summation of forces along y equal to 0. Upward force I am taking positive, it means downward force. Upward force 1. These two are upward forces, Ry plus T sin theta equal to W. That you can take. Ry plus T Sin theta equal to W we are having. Ry how much? We required Ry. T value how much we are having? 830 sin 24.44 degrees. That should be equal to W how much? 35 into 9.81, my dear friends. If I simplify this one, Ry how much we are having? Ry I am having it is a 0. Just to simplify this one, Ry we are having a 0. So, Rx 755.4 newtons. Ry in this case we are having 0. So, which is the required answer? Option D is correct option. Option D is correct option. In option D, Ry we are having 0. So, this is the correct reactions for this given question. Hope you understand this problem. Very long back it is given. 87 question. Read the question. A 6 meter long supported wooden beam of rectangular section 10 centimeter by 20 centimeter deep, that is shown in millimeters in diagram, right? Very good. Is strengthened by a mild steel plates 0.5 centimeter to 10 centimeter wide at the top and bottom. Yes, at the top and bottom. Fiber over the entire length. Very good. Find the minimum supportable uniformly distributed load considering the failure in steel and wood due to the flexion. Very interesting question. By taking the failure in terms of steel as well as wooden, we need to find out the supportable uniformly distributed load on that particular beam. Minimum UDL we need to find out. Weakening of wood due to the screws while we are making the attachment, while we are, yes, composite beams also called as a flitchment. When we are doing the flitchment, whatever the screws we are having, that effect you don't consider, and weakening of the steel plates due to the drilling of the holes also. Because of holes also, yes, the steel plate is as the strength of the steel plate, it is going to be weak. You don't consider that. Only failure you can estimate because of flexor condition only, that is bending condition only. Other data given that, look at here, permissible tensile stress. For the steel, it is given as 156.8 Newton per square millimeters, and permissible tensile stress for the wooden section, it is given as 14.89 Newton per square millimeters, and Young's modulus of the steel 1.96 into 10 raised to 5 Newton per square millimeters, and Young's modulus of the wooden section is given as this one, 0.117 into 10 raised to 5 Newton per square millimeters. Very good. These two are the material properties, and these two, yes, these are also we may consider as material properties because those are permissible stresses in both steel as well as wooden section, right? This is the given diagram we are having. So, when we are analyzing the composite beams or flitched beams, how you are analyzing them? First of all, the given actual beam, I am going to be converted into equivalent single homogeneous beam. That equivalent beam you can take in terms of steel or you can take in terms of wooden. So, how we are converting that? With the help of modular ratio. So, first we are going to be take the modular ratio of these two materials, right? Once I have the modular ratio, I can convert the given actual beam into the equivalent steel beam so that I can analyze that. Very good. Now, let me take how I am taking this one. First of all, see what is a modular ratio. First, I try to find out the modular ratio M. How you can take this one? This is ES divided by EW. How much ES it is given? ES it is given as a, look at here, 1.6 into 10 raised to 5, and this is given as a 1.117 into 10 raised to 5. Let us take this one, 1.6 into 10 raised to 5, 96, 1.96 into 10 raised to 5 divided by next one 0.5. 117 into 10 raised to 5. 10 raised to 5, 10 raised to 5 getting cancelled. 1.96 divided by 0.117, it should be equal to approximately 16.75 we are having. 16.75, that is the modular ratio we are observing. Very good. After that, what we need to do? We need to convert the given beam into equivalent steel beam. So, I am taking for the given beam, just I try to take equivalent steel beam. Equivalent steel beam. So, first I will take the equivalent steel beam. By using modular ratio, we can convert that. How we are taking? We are not doing any changes for the width of the steel. Then it is 100 as it easily. 100 as it easily. But when you take the width of this one, wooden section, you divide that with the modular ratio. Approximately it is a 16. Approximately it is a 100 divided by 16.75. I can take that as a 5.97. I can round off to that is, I can round off to 6 for that one. So, here B, it should be equal to 5.97. That is how 100 divided by 16.75. That I can round off to 6 millimeters. Right? And again, if you take the bottom side, again we are having the steel plate. Yes, we are having the steel plate. This is 5 we are having. This is 100. Here also we are having, this is 5. Now, what about this one? This one, it is given as 200. Let me take this as 200. This as 200, my dear friend. This is the equivalent. That is the equivalent steel section. Let us take the stress diagram for this one. Stress diagram, when I am taking this one, stress diagram. Let us take the stress diagram, bending stress diagram. When I am taking the bending stress diagram, it could be something like this. It could be something like this. This is the neutral axis, just you can assume. Here we are having a neutral axis. Let me take, yes, any one side you can consider. This is very good. Now, this is, if you observe this layer, this is the common layer. This is the common layer for both steel and wooden part. Now, let me take. Wood is available in this portion only. So, here steel, I am sorry, steel is available in this portion only. This is wood part, this is steel part. Steel is available. So, whatever the stress we are observing at this layer, that is nothing but just I am writing a F. F as a, so to represent the bending stress, we can use F or we can use sigma B. So, here F max we are observing with respect to steel. Very good. And if I take this one, when I am speaking the stress related to the steel, here it is Fs. Very good. So, as we know, the stress ratios at the junction of both steel and web, they are equal to modular ratio, as we know clearly. So, Fs equal to M times Fw, but for wooden part, this is extreme layer, na? This is extreme layer. So, with respect to wooden part, the maximum bending stress is available at this layer. Very good. If I say something like this, how I am writing this one? This I am taking 1 by M into Fs equal to Fw M max. That is we are having. Right? Now, this is neutral axis. At what distance we are observing the maximum? At what distance we are observing the maximum stress? Here to here, what is the distance we are having? Here to here, it is 105. Here to here, it is now 100. Very good. This is layer distance from neutral axis, if it is neutral axis. Very good. So, the very first step is we try to find out the moment of inertia for this equivalent section. Since it is I section, you know how to find out the moment of inertia for the I section. I am using that BD cube divided by 12 minus small bd cube divided by 12, that's it. Now outer, this is 100, this is 210 depth. 100 into 210 cube divided by 12 minus, now look at here, 100 minus 6, 94 into 200 divided by 12 we are. That's it. This is the area moment of inertia for the given equivalent section. How much it is having? It is equal to 14.65, I think it is 14.5 into 10 raised to 6 mm raised to 4. That value we are having. That is the equivalent section area moment of inertia. Once I have this one, so first case I am considering if the permissible stress in the steel I am considering. First initially case 1 I am taking. Case 1, by considering both permissible stresses, then we can decide how much amount of UDL I can apply on the beam for the given beam. Now case 1, if I take permissible stress, already given permissible stress in steel, how much it is given, my dear friend? Permissible stress in steel, it is given as, now look at here, 156.8. Let us use this one, 156.8 megapascal. Newton per square millimeters I can take in terms of megapascal. Now, if the permissible stress in the steel, it should be equal to 156.8 megapascal, then what is the corresponding stress we are observing in the timber or wooden section? What is the corresponding stress we are observing in the wooden part? Maximum stress we are observing in the wooden part. You try to calculate this. How should I calculate? Simply, I can use the similar triangle concept. First, when I find out the stress here, Fs. So, in place of this one directly I know that 1 divided by m times Fs we are having. I know the permissible stress for the steel at this layer, maximum stress. With respect to this value, I try to find out the stress at this layer, but that stress I am writing in terms of wooden section. That value I am comparing with the permissible stress of the wooden section. If this value is lesser than the permissible stress of the wooden section, then it is good for us, right? Right, fine. Now, let me take this one. First, I am taking this one, right? For a distance of, just I am taking similar triangle concept. When I am taking this one, F max, it is how much it is given, permissible stress, 156.8. 156.8 divided by 105. 150 from similar triangles. 156.8 divided by 105 equal to, very good. Then you can take this one. This I am taking 1 by m Fs. I am taking 1 by m Fs. Directly I am getting Fw max. 1 divided by m Fs. This is nothing but this term. This term, it is nothing but it is giving the maximum stress developed in the wooden part with respect to this value. If the developed stress is exactly equal to this one, then what happened for the wooden part? That I try to observe this one, right? Then if I substitute this one, m already we know, just you can substitute Fs, or we can say this is, right? Now, how I am writing this one? 156.8 into 100 divided by this one, 105, right? This m I can take this one, 1 by m, 1 by 16.7, 1 by 16.75. 1 by 16.75. How much it is? We are having, just to simplify this one. If I simplify, I am getting 8.915. 8.915, my dear friends, 8.915 megapascal. This is the maximum stress we are observing in the, yes, basically this is the stress available at a steel, with respect to this layer distance, but I am converting that into the FW, that should be equal to FW. So, compare this value with the permissible stress of the wooden part. The permissible stress of the wooden part, how much you are having? 14.89. Let us, this value is less than 14.89 megapascal. So, keep this aside because here it is satisfying. So, when the maximum stress developed exactly in the steel should be equal to this one, the maximum stress developed in the wooden part, it is less than the permissible stress of the wooden part. But suppose if I take a next case, second case, I will analyze this with respect to wooden, permissible stress in the wooden part. How? Let me take that as a case 2, some lengthy question, but long back it is given. Suppose if the permissible stress in the wooden part already given as a 14.89, then what is the corresponding maximum stress developed in the steel? Maximum stress, corresponding stress developed in the steel for this condition. I try to find out this one. Same concept I can use, or you can take for 100 mm, yes, layer distance for wooden part, maximum layer distance, this one from here to here it is 100 mm. For 100 mm, now this time I am taking the stress in the wooden part is for 100 mm. How much amount of stress we are observing in the wooden part? 14.89 we required. Very good. Then for 105 mm. So, extreme layer for the steel part we are observing at 105 mm, right? Now, how much stress we are observing? Let us take this one. How much stress we are observing? That's good. Now, you can take this one. This should be equal to this question mark. It should be equal to how I am taking this one. That stress I am converting into steel part. Is it right or not? So, 105 into 14.89 divided by 100 into m. That stress I am taking in terms of steel, not in terms of wooden part, as we know. Now, if I simplify, what is m value we are having? 16 point, m value it is given as 16.75. 16.75. If I simplify, how much stress we are observing? Corresponding stress in the steel, Fs. Corresponding stress in the steel, if I take this one, 261.87. But a permissible stress in the steel is restricted to how much? This is the stress we are observing in the steel. Corresponding maximum stress developed in the steel. But permissible stress in the steel is going to be restricted to. This is permissible stress in the steel. It is going to be restricted to, that is up to how much? 156.8. 156.8 megapascal only. So, 156.8 megapascal only. We are considering this one. We are considering case 1. We are not considering case 2. We are estimating the UDL load based on this condition, not based on the second case. So, for this condition, you try to observe the bending equation. From bending equation, as we know, bending moment M equal to F into ZNA. F into ZNA we are having, right? So, maximum bending stress for simply supported beam, if I take this one, let us take simply supported wooden beam of length, how much it is given as? 6. Cross-sectional dimensions are given as, clearly, cross-sectional dimensions we are taking for this one, for equivalent section, cross-sectional dimensions. Very good. When I am taking this one, yes, m equal to, you try to find out that. You try to find out that m equal to, stress I can take it as 156.89 INA divided by Y max. ZNA, INA divided by Y max. Already INA we are finding. 156.89 into INA already we calculated. INA for this one, look at here. Here we are having INA 14.5 into 14.5 into 10 raised to 6. Y max 105. This is Y max. From here to here, this is Y max for the given section. So it is 105. This is 105. So this is we are having. So if I simplify this one, I'm having a, how much this is? We are having m equal to, we are having 21.65 kilonewton meter. If you convert this into the kilonewton meter, this value it should be equal to 21.65 into 21.65 kilonewton meter. But for simply supported beam, maximum bending moment we know that for under UDL, but m equal to, I know that omega L square divided by 8. That's it. You can equate that. By calculating, we are having omega equal to 4.18 kilonewton per meter. This is the minimum UDL we need to apply for the given condition, right? Somewhat lengthy this question, but a very long back it is asked. So we try to solve this question based on the two conditions: permissible stress with respect to permissible stress in the steel, with respect to permissible stress in the wooden section. We try to compare the stress magnitudes for both steel as well as wooden section. Then we can finalize the first case. Based on the first case, we are deciding how much amount of UDL we are applying on this particular beam. Hope you understand. Let's move on to the another question. A tapered cantilever beam of constant thickness is loaded as shown in the sketch below. The bending stress will be. Basically, look at here. So here we are applying the transverse load on the beam. Under lateral loads, if you are providing the prismatic beam, it is not having uniform strength. So to maintain the uniform strength, we need to provide the cross-sectional dimensions as per the bending moment available at various sections along the length of the beam. This problem is related to that concept, beams of uniform strength. So clearly that's why in that case, we are not doing any changes for the thickness of the beam. Yes, changes are made only for this one, width of the beam. That's it. So here the width is 0. And here the width is 0 at this end, and here the maximum width we are providing at the fixed support. So the bending stress will be maximum at which options? So bending stress is uniform throughout the length of the beam. It is maximum at a distance of x equal to 2 by 3 times L. It is maximum at a distance of x equal to 1 by 2 times L. It is maximum near the fixed end. That is at the fixed end we are having. So first of all, what is the relation between bending stress and the corresponding bending moment? F is directly proportional to M. So my first target is, we try to find out the bending moment for the given beam. So bending moment is a maximum. Undoubtedly, bending moment is maximum at the fixed support in case of cantilever beams, irrespective of the load. So obviously, the maximum bending stress is available at a fixed support. So option A is exactly correct for this one. But let me take mathematically how you are taking this one. So first to try to find out the bending stress. We will check this one. What is the maximum bending moment available at the fixed end? P into L. That bending moment I can take F into ZNA. How much B we are providing? Just you can verify that. So F into B D square, or you can take a thickness is D, I am taking D square divided by 6 we are having. So how much width I need to provide to make the uniform strength? B you can take it as a subject, then it could be 6PL divided by F into D square. This width I need to provide at fixed support so that we are having the uniform strength throughout the length of the beam. So, option here it is option A is correct for this one. This is the problem related to the beams of uniform strength. Hope you are clear this one. It is also given very long back. Now, this is the first question, simple question. Read the question carefully. Which one of the following diagrams shows correctly the distribution of transverse shear stress across the depth H of a rectangular beam subjected to a varying bending moment along its length? Finally, what they are asking is shear stress distribution in a rectangular cross-sectional beam under transverse shear load. What is the nature of shear stress for any cross-section? If I take the nature of shear stress in beams, it is taking a second degree parabolic variation with a 0 at extreme and a maximum. For rectangular cross-section, maximum we are observing at neutral axis. If I take the rectangular cross-section, the shear distribution for rectangular cross-section, if I take, it is having 0 shear stress at extremities and a maximum at a neutral axis. Here shear is maximum. It is taking second degree parabolic variation. Absolutely. Try to observe the options. It's not linear, it is not constant. Average shear it is taking constant. This is also wrong we are having. Shear always 0, irrespective of the cross section, shear always 0 at extreme points, right? But option B is correct for this one. It's a simple question, shear distribution, right? Now let us take another topic, that is the concept of springs. Frequently from springs, now we are having the question, but very simple question, simple numericals we are having. Now I am taking the topic. Now see the one more question. This is from gate 87, very long back. Try to observe this one question. One more question. The figure shows the arrangement of springs. Here we are having various arrangements in options. They have the stiffness K1 and K2 as marked. Yes, spring stiffness, individual stiffnesses are given. Here it is K1, it is K1, again it is K2, like that. Which of the following arrangement offers stiffness should be equal to 2K1 K2 divided by K1 plus 2K. So that is nothing but equivalent stiffness. Out of these all arrangements, for which arrangement equivalent stiffness should be exactly equal to this magnitude, that is asking. So before I am taking this one, as we know springs we can arrange in two ways, one parallel arrangement, second one series arrangement. So in case of parallel arrangement, for parallel arrangement, how you can find out parallel arrangement, K equivalent, if you take, simply I can take K1 plus K2 for two springs. But for series arrangement, how you can find out equivalent for two springs? When I am arranging the two springs in series arrangement, K1, K2 divided by K1 plus K2 na. Otherwise 1 by K equivalent equal to 1 by K1 plus 1 by K2. These two are the standard formulas we are using. Now here, if I take the first arrangement, let us see the first arrangement. All these springs we are observing under series, yes, connected to each other. All the springs are connected to each other. How you are taking this one? First one, if I take this one, 1 by K equivalent, if I take 1 by K equivalent, if I take this one, 1 by K1 plus 1 by K1 again plus 1 by K2, my dear friends, right? 1 by K1 plus 1 by K1 plus 1 by K2. If I simplify this one, clearly we are having 2 by K1 plus 1 by K2. It is not matching with this one. So option 1 you can eliminate. Option B, if I take this one, these two springs are arranged in parallel connection. When I am taking the equivalent for this one, how it should be? It should be 2K1. After that, these two springs we are having under a series connection. When I am taking the next one for B, if I take for B, equivalent stiffness for series connection 1 by K equivalent for B arrangement equal to 1 divided by 2K1 plus 1 divided by K2. 2K1 we are having. 2K1. Here, look at here. Here we are having 2K2. Need not take that one. Option B is also, you can eliminate this one. Because here we are having 2K2. But we have 2K1. Now come to this one here. Again, if you are observing the option C, option B is eliminated. Option C, all arrangements we are having in a parallel connection. 2K2 plus K1. So it is not matching. Come to this one. Option D. First you take these two springs. These two are parallel to each other. Then it is 2K2. 2K2 is available. Then you can easily pick option D is correct. Then I try to verify whether I am getting that or not. Option D when I am taking 1 divided by K equivalent equal to 1 by K2, 1 by 2K2 plus 1 by K1, my dear friends. Take the LCM. If I take this one, K equivalent equal to 2K1 K2 divided by K1 plus 2K2. We are getting this one. Obviously, look at your asking is also only the same thing. So which option is correct? Option D. For this arrangement, the equivalent stiffness should be equal to 2K1 K2 divided by K1 plus 2K2. So which one is correct for this one? Option D is correct for this question. Right? Hope you understand. Let's move on to the next question. The deflection of a spring with 20 active turns under a load of 1000 newtons is 10 mm. 1000 newtons is 10 mm. So when we are applying a load of 1000 newtons on a spring, the corresponding deflection we are observing it is 10 millimeters. I have initially a spring with how many coils, my dear friends? How many coils? 20 coils, number of coils. Here when I am applying 1000 newtons force, how much deflection it is giving? The deflection, corresponding deflection, if you are observing, it is here to here. Let us mark this as a del. It is given as 10 millimeters. Very good. How many coils initially we are having? How many coils? N equal to 20 active coils we are having. Let us say the stiffness of the spring equal to K. Very good. The spring is made into two pieces. Each it is having 10 active coils and placed in parallel under the same load. What we are doing? We are cutting the spring into two parts. Just we are cutting the spring into two parts we are having. Very good. That two parts are arranged. That two parts are arranged in a parallel position. Initially the spring it is having a stiffness of K. When I am cutting the spring, what is the effect of cutting action on the stiffness of the spring? You try to observe. This is 1000 newtons. Very good. Under the same load. Then what is the deflection in this system? So we need to find out the deflection. In second case, under this condition, what is the deflection we are observing? First of all, what is the relation between K and N? So already we have seen this one. K equal to G D raised to 4 divided by A to D cube N. Standard formula. When you are observing the relation between K and N, it is K is inversely proportional to N. That is nothing but K1 N1 equal to K2 N2. K2 N2. We are cutting the spring into two parts. Then automatically this stiffness it is giving a 2K. This stiffness it is giving a 2K for this part. Obviously just you can substitute. K1 is K, N1 is 20, K2 we require. N2 is 10. Number of coils here it is 10. Number of coils it is 10. 20 divided by 10 it is giving 2K. Very good. From this relation we are having 2K. Then how these two parts are arranged? These two parts are arranged parallel. So try to find out the equivalent stiffness for parallel arrangement. Parallel arrangement, K equivalent equal to K1 plus K2. 2K plus 2, that is nothing but 4K we are having. Then for this arrangement, same load we are applying. Here we are observing 10 millimeter, but here we require this one. So what is the relation between stiffness? Here stiffness it is going to be increased. So, but same load we are having. What is the relation between the stiffness and del? As we know clearly, when I am speaking about this one, K, it should be equal to load by deflection. As we know, stiffness of the spring is inversely proportional to del. You can use this condition. Del 2 divided by del 1 equal to K1 divided by K. We require del 2. Del 2 equal to del 1 into K1 divided by K2. What is del 1? Del 1 it is given as how much? 10 millimeter. This is del 1, 10 millimeters. Deflection in first arrangement. K1 we are having K units. I am assuming stiffness is K. Then in second case, what is the stiffness of the arrangement? We are having 4. 4K we are having. KK is getting cancelled. 10 divided by 4. How much? 2.5 millimeters. So in second arrangement, the stiffness we are observing as stiffness as is going to be increased, the developed deformation is going to be decreased. That's why obviously, yes, option D is correct in this case. Now look at here. If you are observing the relation between stiffness as well as deformation, if the stiffness is increased, the corresponding deflections are going to be decreased. But in option A, option B, if you are observing, look at here, it is again 10 millimeters. That means the deflection remains constant. No, not at all. When I am cutting the spring, its stiffness, it is going to be increased. So option B you can eliminate. So option A is also you can eliminate, because if stiffness is increased, the corresponding deflections are going to be decreased. But unfortunately in option A we are having increase in the deflection. No doubt at all. Option A, option B is incorrect. Either C or D is going to be correct. So like that we can eliminate the options. Hope you understand. Now let's move on to the 2 marks questions. Take the question, read the question carefully. Again, it is very long back question. 93. A circular rod of diameter D and length 3D is subjected to a compressive force F acting at the top point as shown in the figure. Calculate the stress at the bottommost support at A. Here we need to find out the stress value at this point. Now here, this is not related to the torsion question. It is basically combined bending and axial loading problem. Anyhow, we are going to be solve the problem at this moment. F with respect to the cross section, it will be act as an eccentric axial load, my dear friends. Eccentric axial load. When I am converting the effect of F on this cross section, transfer the load to the centroid of the cross section. Load transfer always giving additionally one moment. What is that moment we are having? Now rotational moment, bending moment it is giving. How it is taking the rotation? It is taking the rotation in, see that, like this. Being it is compressive force, then this additional moment we are having something like this. Something like this. Now this is bending moment. 2 effects. Now we are observing 2 effects on the cross section of the rod. One, axial force F with the compressive nature. Second one, bending effect. Take these 2 effects separately. M equal to what is its magnitude? M equal to this distance we are having. The distance between these 2 is d by 2 na? Exactly. M equal to F into d by 2. Good. Now for these 2 effects, we need to find out the stress, resultant stress at point A, that is the bottommost supports. Now try to take the element at this point. When I am taking the element at this point, now look at here. Try to observe the state of stress when I am taking this one. Because of axial force, axial stress is having, what is the nature of axial stress? Axial stress, it is having a tensile or compression. Load is compressive load. This is giving compressive nature stress in x direction. Good. This is sigma axial. Just I am writing sigma A. Now come to the bending effect. Try to observe the rod. Take the rod and try to observe the effect of this M. It is giving anti-clockwise rotation. Because of bending moment, we are having the bending stress. That bending stress also we are observing in x direction. But it is giving a tensile effect as well as compression effect. If I take the deflected position of the beam, now bottommost layers we are observing under tension. Bottommost layers we are observing under tension clearly. Yes, tension we are observing bottom side, compression we are observing top side. But point A lies on the bottommost fiber. So point A is experiencing tensile nature. Point A is experiencing tensile nature bending stress. Obviously, sigma bending, or I can write it as F. F it is having tensile nature. F it is having tensile nature. So because of axial force, we are having compressive nature stress, that is sigma A. Because of bending at point A, we are observing at point A, bending it is giving tensile nature stress. Bending it is giving tensile nature stress. Good. Here we are having compressive nature stress at point A. Try to find out the resultant of these two. Let us take one by one. First, I am taking the effect of sigma F. Effect of, first I am considering effect of axial force F. Due to this, axial stress develops and its magnitude. How to find out? F by cross-sectional area. That is nothing but 4F divided by pi d square, nature compression. Nature is compression. Good. Then take the effect of M. When I am taking the effect of M, try to find out the bending stress. F at A, M divided by ZNA at bottommost fiber. What is M value we are having? F into D divided by 2. Good. F into D divided by 2. ZNA, being it is a circular cross section, 32, pi by 32 dq we are having. That is, simplify this one. You are having a 32 F D divided by 2 pi dq. Good. This is 16 times. This is 2 times we are having 16 F divided by pi d square. What is the nature of this stress? Tensile. Both are in x direction only. Then finally resultant stress. If I take the resultant stress at point A equal to minus axial stress plus bending stress. This is compression, this is tension. This is minus 4F divided by pi d square plus 16F divided by pi d square. Right? Now, 4F divided by pi d square, you can take it as common. Then it is a minus 1 plus 4, na? Minus 1 plus 4 you are having. Just you can simplify this one. 3 4s are 12. 12 F divided by pi d square. That is the resultant stress we are observing at a point A. Here we are having plus. Plus indicates the resultant stress, it is having tensile nature. The resultant stress, we are having tensile nature stress. This is 12F divided by pi d square tensile. See the options. This is a NAT type question. So, this is the final answer we are having. This is the final answer for the given question. This is basically the concept of a combined bending and axial, but we are solving this question at this moment, right? Let's move on to the next question. Another interesting question from gate 93, very long back question. What is the data given? What we are required? You try to observe. The compound shaft shown is built in at the two ends. Both sides we are providing the rigid supports at here and at here. It is subjected to a twisting moment T at the middle point. Now look at here. This is the application of torque we are observing in anti-clockwise direction. Here something like this, anti-clockwise direction, right? With a magnitude of T. Good. The diameter of the first part is D units. The diameter of the second part is 2D units. Length of first part, let me mark, this is a part 1 and this is a part 2. Both are having the same length, and reaction torques at both supports are already mentioned. Then what we required? What is the ratio of reaction torques T1 and T2? So we need to find the ratio of T1 to T2. First, we need to find out the reaction torques, then take the ratios. But how to proceed this one? As we know, this comes under statically indeterminate shaft. Statically indeterminate shafts are going to be stored or analyzed with the compatibility equation. What is the compatibility equation? Here we are having net amount of angle of twist is going to be 0. That is nothing but angle of twist in the first part should be equal to angle of twist in the second part. That is nothing but compatibility. Now I am using that compatibility. Compatibility. Just you can write down. Always indeterminate members are going to be analyzed by starting with the compatibility equation. That is better advisable. Theta 1 equal to theta 2. Theta 1 equal to TL upon Gj for first one, TL upon Gj for second one. Good. Both segments are having same length. Good. And both are made of same material. G is getting cancelled. Right? We required T1 to T2. So you can take this one, T1 divided by T2 equal to J1 divided by J2. That's it. As we know, J for first part, if I take pi divided by 32 d raised to 4, this is pi by 32 2d raised to 4 we are having. That's it. This one is getting cancelled. Then it is 1 by 16 we are having. Final answer, if I take this one, T1 divided by T2 is nothing but 1 upon 16. Verify the options. Again, it is a straightforward question. 1 by 16 we are observing at option A. Option A is correct for this problem. Hope you understand this question, right? Let's move on to the next question. Read the question carefully. Two shafts A and B are made of the same material. We are having two shafts. One is a shaft A, other one is a shaft B. Both are made of same material. Material property is same. The diameter of shaft B is twice that of shaft A. Suppose, for example, if the diameter of shaft A is D, then it becomes 2D. The ratio of power which can be transmitted by shaft A to that of shaft B. We need to take the power ratios between A and B. This is asking. Right? Material is same, but changes we are taking only for this one. Diameters. But What is the relation between diameters to power transmission? See, power, as we know the relation for the power, 2 pi n t divided by 60. That means if I take these two, P is directly proportional to T. And I know T equal to tau into pi by 16 into dq. T is directly proportional. From here, T is directly proportional to dq. That means as T is directly proportional to dq, P is directly proportional to T, I can take this as P is directly proportional to dq. This relation I am using because we are doing the changes for the diameter. That's why I am taking this one. P is directly proportional to D. What we required? This ratio we required. Just to try to substitute the diameter values. PA divided by PB equal to dA divided by dB whole cube. That's it. What is the diameter of first one? D. This is 2D. Simplify this. You are having 1 upon 8. So PA divided by PB, how much we are having? 1 upon 8. Look at the correct option. 1 divided by 8 where you are identifying at number C. Option C is correct for this question. Hope you understand this question. A thin cylinder of 100 millimeter internal diameter and a 5 millimeter thickness is subjected to an internal pressure of 10 megapascal and a torque of 2000 Newton meter. Calculate the magnitudes of principal stresses. Here on the cylinder we are having two effects. One internal pressure effect, the second one is a torque. Internal pressure, it is giving the normal stresses. Torque, it is giving the shear stress. So try to find out this one. So first take the data. Diameter of the cylinder, it is given as 100 millimeter and the thickness of the cylinder, it is given as 5 mm. And internal pressure, it is 10 megapascal. And the torque, applied torque, it is 2000 into 10 cube Newton mm. This is the state of loads and the corresponding data provided for the cylinder. That's fine. We need to find out the principal stresses. Now, because of fluid pressure, we are having the stress in x direction as well as y direction. In x direction, you may consider it is the longitudinal stress. In y direction, you may consider it is the circumferential stress. In addition to that, this torque, it will generate the shear stress. Let us consider the shear. This is a tau xy you can take. Tau xy, if I take, this is a 2T, standard formula we know that for thin tubes, pi d square, sigma L you can take it as sigma x and sigma C you can take it as a sigma y. That's fine. Everything is known, just you can substitute the values. First I try to find out the sigma C. When I try to find out the sigma C, it is a PD divided by 2. P value how much? 10. Diameter 100 divided by 2 into thickness 5. 100 megapascal sigma C. Then sigma L equal to sigma C divided by 2 as we know. This is 50 megapascal. Then tau xy. Tau xy direct formula 2T divided by pi d square T. 2 torque, it is 2000 into 10 cube Newton mm. Pi d square, it is 100 square. T, how much it is given as? 5. If I simplify, you are having just around 25.56 megapascal. Once I have this one, our requirement is principal stresses. Sigma 1 and 2 directly you can find out. First write down the formula. Sigma x plus sigma y divided by 2 plus r minus root over sigma x minus sigma y divided by 2 whole square plus tau xy square. Now, sigma x value how much we are having? 50 na? Yes. 50 plus 100 divided by 2 plus or minus 50 minus 100 divided by 2 whole square plus 25.56 whole square. After simplifying, what is the value we are having? This is 75 plus or minus this term, it is 35.68. So, sigma 1 equal to 75 plus 35.68, sigma 2 equal to 75 minus 35.68. So, this is we are having 39.32, this value we are having 110.68 megapascal. That's it. These are the principal stresses we are observing in this case. This is NAT type question, directly we are getting these values. Hope you understand. Let us take another chapter, that is columns. We try to solve the questions from this chapter. See the first question, if the length of a column is doubled, then the critical load becomes. First of all, what is the relation between a critical load and a corresponding effective length of the column? You try to observe this one. If you are identifying that relation, then we can easily get the answer for this one. Euler buckling load or critical load standard formula, if I take PB cap or we can say PE, it should be equal to pi square E I min, minimum area moment of inertia divided by LE square. So, here change we are taking for LE, that is length of the column. Then what is the relation between PB as well as LE? Inversely proportional, my dear friends. So, if the length of the column is doubled, then what happened to the corresponding critical load? So, to get that one, I am using this relation. Use that relation. In second case, as the length is doubled, this I can take it as a corresponding critical load. I may take it as PB2, then PB1. It should be equal to LE square for first one divided by LE square for second one, right? Then try to rearrange the terms. Then it is PB1 LE for first one L and the second one double. We are doing the doubling the length, then it will be square. It is nothing but 1 by 4 times the initial critical load. Na? That is. So, which one is correct? So, 1/4 of the original value. It becomes 1/4 of the original value. Option B is correct for this question. Simple question. From columns, most of the times we are having simple questions only. Right? Hope you cleared this question. Let's move on to the next question again. For the case of slender column of length L, the flexural rigidity EI built in at its base and free at the top, the Euler critical buckling load. Direct standard question it is. One end, it is going to be built in. Let us take this one. Fixed support, other end it is free, clearly mentioned. At the top it is a free. What is the length of the column? L it is given. Flexural rigidity it is given as EI. So, we need to find out Euler critical load. So, try to find out LE for this one. LE effective length of the column for this one. If I take the buckling curve, join this curve and complete this curve. LE under this case, it is 2L we are having, right? Now, what is the standard Euler formula to find out the Euler buckling load? PB equal to or PB cap equal to pi square EI min divided by LE square. Substitute LE square. Substitute LE square value. When I am substituting LE square value, PB cap equal to pi square EI. I mean I can write it as I 2L whole square. 2L whole square. That is pi square EI divided by 4L square. 4L square. So in denominator 4L square, we are observing at option D. So which one is correct? Option D is correct for this question, right? Most of the times we are having the problems from columns related to Euler formula only.